actually.
Yeah, exactly.
Whoops.
All right. Hello, everyone. Good afternoon, and welcome to the Monday press conference of the Division of Planetary Sciences meeting of the American Astronomical Society here in Knoxville. I'm Shantanu Naidu. I'm the DPS press officer, and with us today we also have Rick Feinberg, who's the AAS press officer. And today we have three great talks. So first, we'll be hearing from Julie Rathbun from Planetary Science Institute. She'll be talking about a closer look at Galileo thermal data from possible Plume sources near Pwyll, Europa. After that, we'll have Glenn Orton from NASA's Jet Propulsion Laboratory speaking about fine-scale waves in Jupiter's atmosphere detected by Juno Cam. And then third, we'll have Pierre Vernazza speaking from Laboratoire Astrophysique de Marseille, speaking about ESO VLT sphere survey of diameters greater than 100-kilometer asteroids, the first results. So before we begin, I'll request everyone to silence your cell phones. After we're done with all three speakers, we'll take questions from those present here and online. So I'll pass it on to Julie. Also, no clapping after the talks.
All right, let's see. So today I'm going to talk to you about a closer look we've taken at some thermal data from possible plume sources in this area of Europa, which is just north of an impact crater known as Pwyll. So I just wanted to start out, let people, see some pretty pictures of some plumes that we have in the solar system. So on the left, you see Io, which is my favorite place in the solar system. And there's some active plumes. This is coming out of a volcano called Tvashtar. And this was taken by the New Horizons spacecraft as it flew by Jupiter on its way to Pluto. The second image is a moon of Saturn named Enceladus, and I think most people in the audience are probably aware of the plumes at Enceladus. There's been a lot of talk about those recently. And then on the right, just to show you one closer to home, I put in an image of Old Faithful at Yellowstone. So there have been some talk about plumes on Europa for quite a long time. When we sent the Galileo spacecraft there back in the 90s, people looked for plumes. They thought there might be plumes. Europa was expected to be active. We're expected to have geologic activity and possibly these plume features. But we didn't see any with Galileo. And so folks have been wondering where they are, what happened to them. And there have been several recent observations looking for plumes from the Earth or from Earth-based observatories. And the first papers that suggested plumes were using a Hubble Space Telescope by Roth et al. And then there were some more recent observations using the Hubble Space Telescope by Sparks et al. That found their observations were consistent with a plume located in this image here of Europa within that green circle. That's where Sparks et al. Found a plume, and they found it in the same location twice. And then there was a much more recent paper earlier this year by Jia et al., which did a reanalysis of Galileo magnetic and plasma wave data that found they were also consistent with a plume, that was consistent with the location that Sparks saw, but that the source location was slightly different. It was a little off. In fact, the figure there of Europa is from the Jia paper, and that blue little teardrop, that's the plume. And you can see that its source location is a little different than the Sparks location of the green circle. So most of these plumes come from hot areas. When you look at Yellowstone where the geysers are, when you look at Io where the volcanoes are erupting, where the plumes are coming from, you see these hot spots. So this image on the left is a Galileo photopolarimeter radiometer image. The contours are telling us temperatures. And it's showing that there are over 50 volcanoes active on Io at this time. And that's, when you look for that Tavashtar plume, when you look close up at Tavashtar, you see a hot spot. You see some thermal emission coming out. When you look at the plumes on Enceladus, you also see warm areas. And that's the image we're showing you on the right. And most folks, I'm sure, have heard of the tiger stripes on Enceladus in the South Pole. That's where the plumes originate. And when you look at them in the thermal infrared, they're warm. They glow. Unusually so. This is not expected. This is endogenic heat. This is heat coming from the body. It's not re-radiated sunlight. So when we look at Europa, one question you ask is, well, if there's a plume, is there a hot source? Is there something warm right where the plume is coming from? So what we did was look at the thermal data to answer that question. There was a paper that John Spencer and I wrote in 2010 where we looked at all the Galileo photopolarimeter radiometer data to see if there were any hotspots on Europa. And we didn't see anything obvious in a global search. We looked at every image that came down of Europa from that instrument and wanted to know if anything was there. However, the PPR instrument, I'll be honest, it's not the highest spatial resolution. It's pretty low. It's really hard to see things that are small in that kind of instrument. So what we did is we did an estimate of like what we could have missed, what would be there that we wouldn't see. We found that in some locations, you could have even a small feature that was 1,000 Kelvin. Really warm for the outer solar system. Typical temperatures out there are more like 100 Kelvin. So this would be really warm out there. And it could be on the surface and we wouldn't have seen it, depending on location. So what we did this time was look more in depth at those two specific locations that Sparks and Jia suggested as being the sources of plumes. And we wanted to look more closely and say, okay, are there hotspots there? So we looked at the data, and in order to really detect if there's something endogenic, something coming from the body, you have to get rid of the sunlight component. Most of what dominates the temperature of a surface is reflected sunlight. And so we had to model how the surface reacted to the passive sunlight, passive reaction to sunlight. And we used our temperature data for this modeling, Galileo PPR, and also some recent observations from Samantha Trumbo at Caltech using the ground-based telescope ALMA. And we looked at this model that considers how the surface responds to sunlight at both of these locations, the Sparks and the Jia location, and found that hotspots were not required at either of these locations to explain the temperature differences between day and night. Day and night, the differences we're seeing in different locations is purely due to the passive re-radiation of sunlight, different thermal inertias. And I like to give the example, if you're at the beach, the sand reacts differently to sunlight than a rock. The sand warms up very fast, cools off very quickly. A rock takes a while. It's nice and cool in the morning, and then it stays warm at night. So that's the kind of thing we're looking for here. So we didn't see any plumes. We didn't see any hot spots. Well, we weren't looking for plumes. We were looking for hot spots. Let me be clear. We didn't see any hot spots at those locations. So why not? Why are there no hot spots? There's several possibilities. One, honestly, is that there are no plumes. That is a possibility. These observations have not consistently yielded results of plumes. And so it could have been some other, something else they were detecting or something else going on with the instruments. Another option is that Europa's plumes are not constant, that they're very sporadic, they go off sometimes and disappear sometimes, and when PPR was looking, there was no hotspot. It could be that Europa's plumes are just different than the ones we see at Enceladus or Io or Yellowstone, and they could not be associated with anything hot. That's possible. Another possibility is that the hotspots are smaller than what we can detect with current data. And we looked much more closely this time than we did in 2010 at the Galileo data and at the ALMA data. And we found that at both of these locations, the Sparks and Ja location, you could have a 100 square kilometer feature that was 170 K, and you still wouldn't see it. The data were not sensitive enough to detect something like that. And that temperature, I used 170 K, that's approximately what we're seeing at the tiger stripes on Europa. So if there was something like that that was this small, we wouldn't see it. However, the tiger stripes are bigger. The tiger stripes in area are smaller than 100 kilometers squared, but they're linear features. So when you look at the PPR data, they should show up in 2 different locations. And we don't see anything like that. That would jump out at us more. If it was linear, it would show up in the data. We don't see that either. So I don't think it's a tiger stripe, but there could be some small source there that we're just not detecting. So I am done.
Maybe go back here. Yeah, yeah. There we go. Right. Okay. Right. Good morning. The Juno spacecraft is currently orbiting Jupiter in 53-day period orbits, highly elliptical, getting very close to the planet in polar orientation. Part of the, one of the instruments on board that spacecraft is Juno Cam, which was intended as a public outreach camera, returning resplendent images of the planet's atmosphere. Truly stunning. They are being sent out to the public for their own type of processing. That processing is coming back, and that's being released immediately. Now, part of that treasure is, in fact, many points of scientific interest, and what I'm going to talk about is one of those. We've discovered a huge number of very small-scale waves in the atmosphere. You would typically call these mesoscale waves in the Earth's atmosphere. I'm not quite sure what applies to Jupiter, so I'm just calling these fine-scale waves. You can see on the background here an example, one of those on Perijove 14. Perijove is one of our close approaches to the planet. We're getting about 3,500 kilometers from the planet, allowing us a great deal of very close-in perspective on the planet. So JunoCam is picking up, this is the 3-color camera. It's not calibrated, but showing these really great images. And here are examples of the types of waves we're seeing. I'm using little combs with fine teeth to show you the wave train itself and the types of waves that we see in each one of these. On the screen, these may be hard to see. They should be okay on the press release or on this presentation. Here, for example, in panel A, we have a rather typical set of waves with a wave train that's parallel to the equator, going at pretty constant latitude. And on the wave fronts, you can see are pretty much perpendicular to that wave train. Another set of these, for example, is a tilted wave with wave fronts that are not quite parallel, but tilted, sometimes in very different directions. And sometimes the wave train is shorter than the wave extent. Up here we see in panel C, one of these really short wave trains with very long and somewhat arcuate waves that are crossing, in fact, another set of waves that are sort of superimposed waves in the atmosphere. We have many of these near the equator that are replete with wave properties. And some don't fall into those categories. They're curved. We see in panel D a set of curved waves that are maybe converging, and you can see wave fronts that appear to be following this thing, possibly a flow line. and they're either superimposed on or maybe overlying those waves. One of the waves that's rather very interesting is the fact that we see Lee waves. Here we are in that a very dark region just north of the equator called the North Equatorial Belt, right in the middle of it. Here during perigeo 14, early February 2017, there was a big outbreak, a plume that we see in white here, and you see flow lines going around that, and right on top of those flow lines look like 3 waves. One of those waves seems to have a dark feature. In fact, the fact that there are dark features on all of these things, and the fact that the sun is only 10 degrees above the horizon, gives us rise to think that that may indeed be a shadow. The 40-kilometer length of this shadow gives us the impression that with that solar angle, we're seeing something that's 7 at the side and maybe 10 kilometers at the peak of the wave above the background cloud system, which is somewhere between 1.2 and 1.5 atmospheres of pressure in the atmosphere. So we have a resplendent series of these. What are these from? Just like we see in the Earth's atmosphere, we have some sort of distribution, one perturbation of the atmosphere. When that material is lifted up, we see material like water that condenses into clouds. In Jupiter, this would be probably ammonia. That's upper level condensate in the atmosphere. And then gravity, sometimes they call it gravity waves or inertial gravity waves. These things sink down again in equilibrium, and then they just rise up again, oscillating back and forth. So every time we see that peak, we see a condensation in the Earth's atmosphere. We see a long set of waves with shorter wave trains that are not quite perpendicular, but kind of closer to that. We see again, this example there, sort of long arcuate waves with a very short wave train and long wave fronts. And here in this satellite picture of the Sandwich Islands, we see Lee waves. That is things encountering obstacles that are flowing around it and then bouncing up and down and causing these condensate levels. And there's one thing we see in the atmosphere that was really astonishing. There's one example we have of clearly a cyclonic region. This is counterclockwise in the northern hemisphere. And outside of it are these kind of spoke-like looking things, which have some resemblance, not perfect by any means, of these sort of spokes outside of another rather infamous cyclone, which is Irma from last year, 2017, in the Caribbean. Now, these are all pretty pictures, but we try to make some sense out of this. We take some measurements as well as the pretty pictures themselves, and we see some sort of organization. We see all of the observations we made in this study from Juno Cam itself are in black. The previous measurement set that had found this many waves was way back in 1979 with Voyager. We're currently passing their total number of waves they've seen, and their waves are here in blue. So if you have like any broad hand-wavy analogy, we'd say the waves that we see in Voyager are closest to the ones that we're seeing here. Except we see 2 clusters. Voyager saw a lot of waves right at the equator. Here we're seeing clusters of waves, and we're plotting the length between wave fronts, I'm going to call it the wavelength, versus latitude. And there's a cluster here and a cluster here. 2 things to note, except for waves up here that are rather long and down here, both of which are mostly associated with big vortices that are causing perturbations. All of the waves are located in parts of the mean flow, the flow from east to west, west to east, that are prograde, that are going in the same rotation as the planet. This is telling us that it's probably just hard to make waves in the retrograde flow of the atmosphere. The other thing is that these 2 clusters appear, at least certainly in one of them, appears to be in a location which is coincident with the upwelling which is seen from the microwave radiometer. And the second cluster is associated with possibly a minor upwelling as well. And so we're slowly going to piece together, we're starting on that journey of what these waves mean. Other waves you've seen from missions from Voyager New Horizons or from the Jupiter Infrared Auroral Mapper, JIROM, which is sensing things at 5 microns waves, which doesn't have the resolution that we're seeing with JunoCam. We're seeing very big waves. And you've seen from New Horizons and HST very big waves as well. So we've now gotten the inventory of waves with JunoCam down to very small numbers. But in fact, we should have been able to see waves in this range between Voyager and the Juno mission, and we don't. So we're in this period like Voyager of lots of waves in the atmosphere. And there are times, for example, when the Cassini mission went by, it did not see any waves. So we're now discovering sort of different modes in which these waves are prevalent in the atmosphere and sometimes when they're not. And that's going to be telling us something. We don't know what it is yet, but we're watching, and we're going to be watching on for the remaining orbits of Juno. We've stopped this study at Perigeo 14 pretty arbitrarily, just because we needed to say something about the waves that we've seen so far. Anyway, that's what we've got. Right, thank you.
Okay, hi. So we'll present first results and images from the VLT sphere survey of asteroids, of main belt asteroids. So I don't know if you're familiar with the sphere. So it's the current new generation imaging system at the VLT. And the combination of this imaging system with VLT makes it the most performant imaging system currently in the world, Earth-based system, including HST. And it provides the highest angular resolution for today. So what we're doing, it's a survey of asteroids with the sizes typically larger than 100 kilometers in size. We obtained a large program over 2 years that started last year. And we're surveying basically between 30 and 40 objects throughout their rotation in order to derive their density. So why do we focus on 100 kilometer sized bodies? Because these bodies are considered as primordial. They're not seen as typically rubble piles that are the leftovers of large collisions, and where basically the primordial internal structure would have been lost, at least information, and we try to focus on large bodies for which the latter would still be kind of intact. And it's also a good occasion to witness the surfaces of primordial bodies, how it has evolved via impacts over the age of the solar system. So there are roughly 200 bodies with diameters above 100 kilometers in size in the main belt. And for these bodies, we have a very good characterization of orbit albedo and even surface composition, but actually we have very few constraints regarding the surface, the geology, and the geophysics for these bodies. So far, the only precise constraint we have obtained for main belt asteroids, and asteroids in general, including NEAs, are via dedicated in situ missions, either rendezvous mission or flyby missions. So when you look at the largest ones, the bottom, like Lutetia, Sirius, and Dawn, Vesta, you just have 3 bodies that have been seen close. And so for the remaining 2 bodies, we have basically very little information. So basically the output of the survey is to collect 3D shapes, precise 3D shapes, and hence volume for these bodies that we, once combined with mass estimates, gives us the density. And also the accuracy of the images allows us to start mapping craters from the ground, which wasn't possible before, as you will see in the next series of slides. So we'll just start with Pallas. So on the right, it was Pallas imaged by the former imaging system at the VLT NACO. And on the left with the new generation system. So as you can see, I mean, it becomes a world to which we can give a face. I mean, we see the craters. So we have a roll rotation, 6 to 7 epochs, and we really can map the craters and consistently find them throughout the rotation. I will show you another example here. So where we start to compare actually ground-based data with respect to in situ data. So here, just to give an idea, so this is Lutetia on the left, imaged by the Rosetta spacecraft 70,000 kilometers away during the closest approach. And on the right, it's 7 Iris, which is 200 kilometers across. So to some extent, the data is comparable in the sense that you can start mapping the largest craters. So one can really appreciate the progress that has been made from the ground. Obviously, I'm cheating. I mean, the closest approach with respect to Lutetia was 3,000 kilometers away. So then the images obviously were more spectacular, but one really can see that we are from the ground approaching a kind of data quality that is obtained from far flybys. So here I will show you a Vesta seen by Sphere on the left compared to a synthetic image produced using the OASIS model. So the latter uses the 3D shape model from the Dawn mission and recreates a synthetic image with the same pixel sizes, etc., as the Sphere instrument, so it kind of produces a perfect image. And as you can see, one can very well recognize the main features like the Rhea Silvia mounts on the South Pole, and also craters that have sizes above 25 kilometers that are highlighted with the boxes. And so same thing, so we consistently found the features throughout the rotation. In the case of Vesta, as you can see, the contours are perfectly clean. And so it allows you to appreciate the progress that's been made, especially, I mean, I'm not showing HST images, but I mean, there's significant progress made with respect to that. So here quickly I show you the big four, so the Ceres, Pallas, Vesta, and Hygiea seen by sphere, so all bodies with diameters above 400 kilometers in size. So Hygiea is like Ceres' little brother, sister, depending how you want to see it. It's the only asteroid in the asteroid belt that has the same spectrum as Ceres, and density is extremely similar. So there are two unique bodies, but must be linked genetically as they have really the same surface composition and internal structure. I mean, at least surface density. And as maybe you get a quick glance, I mean, Ceres and Hygiea surfaces look really smooth, for example, respect to Pallas. So it already gives you hints in terms of differences in terms of surface composition and response to impacts. So most likely Ceres and Hygiea have more water ice on the surfaces, which relaxes the outer topography with respect to Pallas, which has certainly less water, and the crater stays stable at the surface. So I quickly will show two first results that have been published already, at least that are under press. So regarding, on the one hand, the asteroid Julia, which is a nest type roughly 140 kilometers across. And for that body, a small family was discovered a few years ago by David and Swan et al. And reported, comprising 30 members. We redid the dynamical study and found 30 additional members. So it's basically a family comprising 66 members with very small diameters below 2.5 kilometers. And by doing simulations, we showed that this family must be relatively young, with an age between 30 and 100 million years. And that it was created following the impact of a small object, roughly 8 kilometers in size, that left a footprint of at least an impact of at least a diameter with a diameter of at least 60 kilometers. And we had a very good surface coverage via our images of the asteroid, like more than 99% of its surface. And we only found one large crater, which is shown Vernazza, with a diameter of 75 kilometers. So likely we imaged the impact crater. And as a matter of fact, the location would be pretty consistent with the current location of the family in the orbital plane. And finally, very quickly, I will move to Psyche, the target of the Dawn mission, the Psyche mission, sorry, of the future NASA Discover mission. So that the very first images of Psyche with sphere on the bottom. So the upper two rows show the corresponding shape models. And so currently, we had, it was pulled on, so basically what you see is the image is just, it rotates in the same plane, let's say, but we can distinguish already albedo features, a likely impact crater, it's the dark spot that you can see surrounded by a yellow line. So importantly regarding Psyche, it was sold as an iron metallic world. The density doesn't agree very well with that, so we found that we obtained a density of 4 grams per centimeter cube, quite far from the typical density of iron meteorites. It looks more similar to mesositerites, and actually the spectrum looks also closer to mesositerites than purely iron meteorites. So perhaps we're seeing a world that is perhaps more silicate-rich, but it remains anyway very fascinating targets, because the formation of mesositerites remains an entire mystery. So I leave you with the conclusions, and as soon as the data are published, we put them available. So thank you online. Thanks.
Thanks to the speakers. And we'll take questions, but when you're asking a question, please state your affiliation clearly and then ask your question. Your name and affiliation. Yeah.
Hanukkah Weidering with Space.com. My question is for Glenn. I'm wondering, what can these little waves reveal about what is perhaps underneath the outer layers of Jupiter that we can't really see yet?
Right. Waves can be generated by, the wavelength may have something to do with the depth of the wave, and so part of the structure and the composition of the wave. That may give us some clue about what's taking place. The correspondence between those waves just north of the equator that are so resplendent right there, highly populated, may be telling us something about the structure of the atmosphere as this material is running up from great depths. The fact I hadn't pointed out, the fact that there may be something that because we don't see waves between 5 south and 15 degrees south, may be saying something about the static nature of the atmosphere there as well. So it may be revealing something both about the depth of the stability of the atmosphere and the strength of the dynamics as well. Okay.
Are there any online questions? Okay. Nola?
Oh, we have another one here? Okay.
Nola Red, freelance. So for Julie, you mentioned the possibility that there could be plumes generated without a heat source. Like, are there any ideas about how that could happen?
I am not aware of any ideas of how that can happen, but I am constantly amazed at how many things we find in the outer solar system that don't make any sense. And so I like to leave it as a possibility because, yeah, I mean, there's so many things out there that were not as expected. So it's possible.
Luca.
Hi, Luca Maltagliati from Nature Astronomy. Still for Julie, you presented at the end 4 possible scenarios why there is kind of apparent discrepancy. What do you think is the most likely? If you can, I know it's difficult, but.
It's incredibly difficult to say which one is most likely because we don't have the data, right? So it's mostly guessing at this point what's most likely. And I could go back to my answer to Nola, which is, which do I want to have happen? And I'd love it if it was something different going on. I mean, that's always the most fun part, when there's something you don't expect happening. So that's kind of what I'm hoping for. As for what I think is happening, or what I would make a bet as to what was happening, I mean, we depends on the day of the week, time of day, who I just spoke to.
Okay, we have a question online from Camille Carlisle at Sky and Telescope. This one's for Julie. She says, I'm confused. I remember there being evidence of a hot spot before, previously teased out of Galileo data. Was that discovery dismissed?
So if I understand correctly, I think she's referring to the Sparks paper. When Sparks first found a plume source from HST that was in the same location, and they looked at the PPR thermal data, they found a region just north of Pwyll that was a little warmer than the surroundings. However, that observation, let's see if, trying to explain it without the image. In that observation, that was a nighttime observation, and so it was slightly warmer. There was this big region that was maybe a degree warmer than the surroundings. That could very easily be explained by these passive thermal changes. And what you really need to really understand these passive thermal changes to sunlight is to have an observation during the day and an observation at night. PPR did not get a very good daytime observation. We got a great nighttime observation. ALMA got the daytime observation. And when you combine the ALMA observation with the PPR observation, the high temperature region during nighttime is cold during the daytime, colder than its surroundings, which is much more consistent with a difference in thermal properties than with a difference, than there being a hot spot, than there being some endogenic activity coming from itself.
Okay, and I actually have a follow-up myself, then we'll come back to the room. This is Rick Feinberg, AAS press officer. So I was curious what it would take to resolve the uncertainty in which of these interpretations might make the most sense. And I'm wondering if that's something that James Webb might be able to resolve fairly straightforwardly, or if you need to do another space mission to Europa.
I am not as familiar with James Webb as I would like to be to answer that question. I am on the Europa Clipper E-Themis team, which is a thermal instrument that will be flying on Clipper, and we will definitely get the data from E-Themis to resolve this. E-Themis is improving our spatial resolution in terms of the thermal data on Europa by 2 orders of magnitude, by a factor of 100. So if there is a hotspot somewhere on Europa, then E-Themis will see it.
Hanukkah Widering with Space.com again. I have a question for Pierre. I'm wondering, of all of the asteroids that you have mapped, is there one that stands out to you as particularly interesting for another asteroid mission in the future, or maybe just a personal favorite for any other reason?
Several ones, I would say, yeah. So I didn't show Cleopatra, which is very untypical, so we could resolve this object, which is a dog bone. I don't know if you are familiar with Cleopatra, and we see that the 2 lobes are not in contact, so suggesting a prominent neck. So for instance, that's very peculiar. It's very difficult to explain via formation. It's not trivial, so we have no explanation for that currently. Doesn't work. Bon. Okay. And otherwise, yeah, so we have observed IGA, so the 4th largest one, and it has the largest family associated currently. And we are not, it's not obvious for us where the large impact crater is on the surface. We don't see any outstanding evidence for it, as we can see for Vesta, for example, or even Pallas. So, and Hygiea, the Hygiea family is really the most prominent one in the asteroid belt. So that's also untypical. Perhaps it can easily be explained by relaxation. The impact occurred a very long time ago, but it's also a mystery. But many new questions that emerges via this imaging survey. So.
Did you have a question back here? Yeah, Carrie.
Amanda.
You don't have to.
Hi, Amanda Hendricks with PSI. I had a question for Pierre also about Hygiea, because it sounded like you were comparing Hygiea to Ceres. And can you say a little bit more about that? Are you saying you think they're related?
When I said, yeah, genetically related, so they have really the same spectrum from visible to mid-infrared. So throughout, it's like, so even in the 3 micron region, they have this similar 3.0067 micron band. So they're very similar on all scales, and even the density is nearly the same. So you can't distinguish them on any basis of the density, so internal structure or surface composition. So they really seem to be identical in terms of composition and less likely in terms of origin. And yeah, okay. And then there's no other known asteroid that has the same spectral properties as those 2 guys. So.
Okay, cool.
I have another question. Oh, sorry, Nora. No, we'll come back to you. This is actually from me again, Rick Feinberg, AAS press officer. This one's for Pierre. So I'm obviously impressed, as I'm sure we all are, at the quality of these images. I'm wondering what you see as the prospects for near-Earth asteroid, near-Earth object characterization with this system, or is there something about how fast such objects are moving that would make it harder, for the system to be able to observe those?
Well, they are really, so first of all, the fact that they are so fast is a problem, and second, their angular resolution is really small. So here we're dealing with objects that are 0.2 arc seconds. It's nearest us asteroids are like 0.001 or a factor of 20 or 50 smaller. So you would cover them with a few pixels only. So you wouldn't have those spectacular images for those objects, unless they come extremely close to the Earth. But then again, then you have the problem of the speed, and it means they are really fast. So it won't be easy for those objects.
Nola?
Nola Red again. So for Julie again, I'm wondering, would it be possible to have like multiple smaller holes that would produce the plumes and not see a heat signature?
Trying to think about the modeling. That's kind of similar to what is seen. The tiger stripes on Enceladus, there are hotter areas along the tiger stripes. This is work John Spencer and Carly Howard have done with the Cassini-Sears instrument, looking at the heat sources on Enceladus. But even so, even with the spots of hotter stuff, it's still sort of warm in between. That and, well, the other thing with Enceladus is that there's even some background heat flow from in between the tiger stripes. So there's sort of a lot of heat coming out there. But of course, it could be different than what's going on in Enceladus. If there were lots of little tiny ones, again, it depends on how hot they are. The limits I gave you an area and a temperature. Of course, if you're willing to let the temperature go down, the area can go up. And if you're willing to let the area go down, the temperature can go up. So it's a give and take there of what could be in the data and hiding that we just wouldn't have detected. So as long as it added up to less than about 100 square kilometers, it could be in the data. And as far as the modeling goes, I'm not entirely certain.
I had a question for Pierre. So there was a radar shape model for Psyche as well, and you have a shape model, right?
Yes.
Do you see any similar features or similar shape?
For now, they are very similar. So,
Okay.
But at the same time, Psyche was pulled on, so we always saw the same area. So it's difficult to confront for have a global shape model. I mean, for other regions, but from this aspect angle, it's really very similar.
Okay. All right. Okay, Amanda.
Thank you. This is for Julie. You know, we think about comparing Europa a lot to Enceladus, but maybe it acts very differently, right? And maybe the cracks that we seem to see on the surface of Europa are a red herring, and not tiger stripe like at all. And so, do you think about comparing Europa's possible activity with Io's? Even though, you're not seeing any hot spots, but is there any comparison to be made there?
I guess the only comparison I can think of is with the chaos regions. If the chaos or the things that are called lenticulae, spots, pits, and domes, are actual cryovolcanism. Because the way some of Io's plumes are formed is that as the lava reaches the surface, and in Io's case, of course, it's silicate, not ice. As lava reaches the surface, it melts deposits of sulfur dioxide frost that are on the surface. Not only melts them, it sticks them straight into the vapor phase and they go flying. That's how you get a plume. I don't know that anybody's looked at how to do that cryovolcanically. Could you have had a cryovolcanic flow on the surface that somehow remobilizes some kind of frost? That's actually a good question. I don't know that anybody's modeled anything like that or looked at it. Yeah, and I think the cracks are hard because, as I said earlier, yeah, you would see a thermal signature that was extended, and so it would be easier to spot. But something with that, and the reason for the 100 square kilometer size I gave is because that's the average size of those lenticulae. They're about 10 kilometers in diameter, so about 100 square kilometers. So that was our original thought. That was before sort of a lot of the Enceladus stuff came out and a lot of the tiger stripe stuff came out when we were thinking just about Europa. Our original thought was the lenticulae as being the source. All right. I sort of answered it.
All right. Yeah.
There are no more questions online, but I just wanted to point out that we have posted a press release from Planetary Science Institute in support of Julie's presentation, and Glenn Orton has a press release kicking around at NASA headquarters waiting for final approval. And as soon as we get that from JPL, we'll have that one out. And as of right now, we don't have anything from Pierre. Okay.
Yeah. All right. Thanks to everyone who presented and everyone who's here. There'll be another press conference tomorrow at the same time, 12:15 here. So hope to see you there. Thank you.